Hi, today we're in class and we're going to look at acids and bases. We're going to go over the work that was done in Level 2 NCEA and introduce some new ideas for Level 3. Okay, so definition of an acid and a base. When acids react, they produce H3O plus ions. So we can see here we've got a generic acid. It's called HA. It reacts with H2O or water to produce hydronium ions. The reaction that actually happens here is that the acid donates a proton that is a hydrogen atom that's lost its electron, so it donates a proton. It's a hydrogen atom and a positive charge to the water, and that's how come the water becomes a hydronium ion, because it's donated H+. When bases react, they do the opposite, right? So a base here, just calling it B, is going to accept a proton from the water. So here we can see that the proton is being accepted by the base. This makes this thing here a base. Once the water has donated its proton, it becomes hydroxide ion because it's lost a hydrogen and a positive charge. If you're neutral, lose a positive charge, you become negative. If you're neutral and gain a positive charge, you become positive. Right, so that's introduction. Strong acids. So we have something called a strong acid. It is a particular type of acid that when it reacts to completion. So an example here is hydrochloric acid. So what the hydrochloric acid does is it has an arrow that says all of the reactants turn to all of the products. So in this case, we get all of the hydrochloric acids can donate to water to produce, whatever amount of hydrochloric acid we have is going to produce the same amounts of chloride ions and the same amounts of hydronium ions. So we can say that the amount or the moles of hydronium ions is equal to the moles of the acid. That happens because of all of the acid reacts to produce an equal amount of H3O+. Yep, so if this here was a concentration of 1 mole per litre, this would be 1 mole per litre. The other thing to notice is, see this chloride here? This chloride is sitting right next to a very strong acid particle. This hydronium ion is called an acid particle. But since the chloride won't react with the acid, the chloride is not a base. In fact, the chloride here is a neutral substance. Whenever a strong acid reacts with water, the ion it produces is always neutral. It's neutral in terms of acid and base, it's not neutral in terms of charge, correct. So here are some examples of some strong acids. So we've got sulfuric acid, H2SO4, hydrochloric acid, HCl, nitric acid, HNO3, and phosphoric acid, H3N. Wow, that's spelled wrong there. I'm going to have to get in and change that. That should be H3PO3, phosphoric acid. Let's make a correction for that. One thing to notice about these strong acids, they all have an H on the left-hand side. Those H's are what are being donated, okay? And if we look at this, SO4, this sulfate ion that's going to be produced is going to become a neutral ion. It's going to be a neutral ion because it's made from a strong acid. The nitrate ion is a neutral ion because it's made from a strong acid. And this corrected one here, this phosphate ion, is going to be a neutral ion because it came from a strong acid.
So the strong acid becomes neutral.
Yeah, so the ion produced from a strong acid becomes neutral. But in the same instance, we make this acid particle, right, which is the hydronium ion. But this one here is an acid, yeah? So there are some acids, H2SO4 and H3PO4, that have the ability to donate more than one hydrogen. So what will happen to this sulfuric acid? It will donate a hydrogen to water, and then it will do a second step where HSO4 minus donates another hydrogen to water. Yes, we would write H3SO4 plus 2H2O gives us SO42 minus plus 2 of those. It would produce twice as much. Exactly. When strong bases react with water, they react in a slightly different way. So what you can see here is a strong base is actually here, in this case, sodium hydroxide is an ionic compound. So this would be a solid. And what happens, we place it in water, it disassociates, it breaks apart. It actually has this OH minus ion as part of its lattice, and it just breaks apart into the base particle, the hydroxide ion, and these sodium ions. This, the amount of OH produced is equal to the proportion of OH on the left-hand side. So in this case, we get one, if we have 1 mole per litre of sodium hydroxide, we'll get 1 mole per litre of hydroxide. However, if you look down at the bottom of this table, if I had used calcium hydroxide, I would break that into 1 calcium 2 plus and 2 OH minus. So I would get 2 OH minus for every 1 calcium hydroxide. So sometimes you get double the ratio depending on what you have. And that's what I put down on this wee reminder here, that barium hydroxide and calcium hydroxide can produce twice the moles of OH minus, because they produce 2 from every 1 ionic formula here. These ones are all ionic compounds because, yeah, strong bases here. Well, in this case, the ones that we're looking at are all ionic compounds. Sometimes bases aren't ionic compounds; they're molecules like ammonia. Yes, sometimes we get bases that just accept a hydrogen but don't do this special reaction. Yeah, so in this type of thing, what we would say is the actual base is this here, this OH, this is what's going to accept the hydrogen. What we're saying is if we put this solid in water, we produce this base and this. So we just say, hey, this really is a base, because in essence, the OH minus will go on and accept the proton. Yeah, this part here will accept the proton. This, we don't show it doing that. We just show the initial reaction of it breaking apart. Then later we would say, but the OH reacts with this, it accepts the proton. Okay, if this accepted a hydrogen and a positive, what would it become? Exactly, it would become H2O water. Okay, so next one. Conjugate pairs. Okay, so that was strong acids and strong bases. We're now going to look at something called conjugate pairs. Okay, so a conjugate pair. So in this topic, majority of the time, we're going to be looking at acids and bases that have an equilibrium setup. Hence the topic's called equilibrium or aqueous chemistry. So what happens is if I take this substance here that is an acid and add it to water, it's going to do what an acid does. So what an acid does is it donates its proton. Cool? It goes across to make this new species that has lost the hydrogen and lost a positive charge. So it was neutral, it becomes minus, it's lost a positive charge. It was H2, it now becomes H. So we can see that this is an acid, right? Because it's donating its proton. Therefore, what it turns into is going to be a base. Now, how can you see that this is the base? Well, look at this. Because this is an equilibrium reaction, this goes backwards, we can see that the H3O plus has donated a proton in order to become H2O. So when we go backwards, in order for that to become H2O, it needs to donate a proton, and that accepts the proton to become this again. So on this case, on this side, H2CO3 is an acid because it will give away a proton. On this side, HCO3 minus, it's the base because it accepts a proton to go backwards. These two yellow ones are called a conjugate pair. They are a pair, and the only difference between them is a hydrogen and a positive charge. Can you see another conjugate pair? So, right, the other two are a conjugate pair, this base and this acid. So water and hydronium ion are a conjugate pair. This is the acid, water is the base. Okay, so we have these things called conjugate pairs. So if someone gives you a molecule and they say, what is the conjugate acid of this? What you do is you just add an H plus to work out what the acid would be. If they give you a molecule and they say, what is the conjugate base? You would subtract an H plus to work out the base it would become. So these two, conjugate pair. Notice that these are also a conjugate pair, and the difference is an extra pair. I just talked about that. The other thing to notice about an equilibrium when we have an acid reacting with water is that on either side there's always an acid and a base. You don't have two acids or two bases. We're always reacting an acid with a base to go forwards, an acid with a base to go backwards. So we have on either side there's an acid and a base, but also across the equation we can recognise the two that are only an H plus different from each other. They're called a pair. One of them is an acid and one of them is a base. Exactly. Yep. So one will be one more hydrogen, one will be one less hydrogen. Okay, amphoteric. Okay, or amphiprotic, sometimes called amphoteric, depending on the exact definition. So we saw in their previous slide that water acted as a base, right? So water can act as an acid as well. In this case, water is acting, in this case, let's just not talk about water, let's talk about this carbonic acid, right? When it reacts with water, it becomes this here. So we can see that in this case, this substance here, when it goes backwards, is acting as a base, right? HCO3 minus is a base because it accepts a proton to go back to H2CO3. In this next equation, look at this here. HCO3, when I add it to water, it donates a proton. In this case, this is acting as an acid. How is it that this species can be a base sometimes and an acid sometimes, other times? This is what amphiprotic is that they can be an acid and a base depending on the situation. What happened here, this substance, hydrogen carbonate, I put it with this acid particle, in that case it was a base, right? So this is, we could say, more acidic than this, so it's going to donate its proton. Which one? This one? This H2O must be a base here, but it's also a base here. But I'm looking at this HCO3 minus. See how it's acting as a base? When I put it with H3O plus. But when I put HCO3 minus with H2O, it acts as an acid. So in some situations it can be an acid, and in other situations it can be a base. Exactly. So it's a species that exists in another form with an extra hydrogen and a positive charge, but also exists in another form with one less hydrogen and one more negative charge. So we see that this can exist as carbonate or it can exist as H2CO3. So therefore it becomes amphiprotic. Now there's quite a few of these substances around, so not all substances are defined as just an acid or a base, but they're defined as something that could be an acid and a base. Water is a prime example of this because H2O can go to OH minus or H2O can go to H2O plus. It can either act as an acid or as a base. So one peculiarity about water is if water can act as an acid and a base, can it react with itself? So here's an example of how water acts with itself. So here's water acting as an acid and water acting as a base. Yeah? So this one donates a proton, this one accepts it. So if we take a sample of pure water, this reaction is happening all the time at equilibrium. This reaction, water is always producing negative and positive ions. If you look in a glass of water, you're always going to have base ions, you're always going to have acid ions. I know you're going to tell me, but hey, isn't water neutral? Yes, it is. So how can water both have acids and bases and be neutral? Exactly, equal concentrations of OH minus and H2O plus means water is neutral. It doesn't mean it doesn't act as an acid sometimes, and it doesn't mean it doesn't act as a base. The other thing about water is water always has some ions hanging around because it makes its own ions. So it conducts the electricity just a little, not perfectly, because there's only a small amount of this made. In fact, if we draw the Kw for water, equilibrium constant, we don't include H2O because their concentration is constant, so we just put the products, Kw equals OH minus times H2O plus. It actually equals 1 times 10 to the negative 14 at 25 degrees. Okay, that's the value. So that means the amount of products is actually quite small. It's a very small number, right? So this must, in fact, here's the point. If that equals that, they must be the same, right? So 1 times 10 to the negative 14 must be the concentration of OH minus plus H3O plus. Exactly. So it's similar to the Ks. We just put the products. Okay. But we need to remember this value. This value never changes. The Kw for water is always 1 times 10 to the negative 14 at 25 degrees. If it gets hotter, the Kw gets bigger. So, but we put these two together, and I get rid of the Kw, and I get that the concentration of OH minus times H2O plus equals 1 times 10 to the negative 14. What's more interesting than that? What would you say about the concentration of OH minus and H3O plus if you had pure water? What would they be like related to each other? They would be the same. So I can simplify this equation. Well, I didn't actually do this. I can't actually go backwards. So what it means is that they are the same, right? So there we get 1 times 10 to the negative 14 equals right, pH. How do we work out pH? So sometimes you get an H2O plus concentration, which is actually just the H plus concentration, written in another way. It could be 1 mole per litre, it could be 1 times 10 to the negative 4 moles per litre. So we get this huge range in values, and it's quite hard for everyday people to interpret those numbers quickly. So instead of using that, we use a scale of 1 to 14. And the way we do that is we apply a log function to these numbers, and we make a negative log function. So you'll see what happens here. So if I want to represent the concentration of H2O plus, I carry out a log function to make it a similar number. So remember, a log function takes the exponent and uses the exponent to produce the number. So here's the equation we need to use here. So if I want to find out the pH, we letter P in front of H means the negative log. We take the concentration of our H plus or our H3O plus, and we carry out a log function to it, and then we change the sign of it to make it positive. This equation here, by the way, is fundamental, is one of the 3 fundamental equations we need to know for this topic. You just need to be able to do this really quickly without thinking about it. So you need to practice doing exercises with this on your calculator. If we rearrange this equation, now how we rearrange this equation is the opposite of log, I think, is 10. Let me get this right. Let's look on my calculator. Opposite of log is 10 to the x. On your calculator, you press shift log. Okay? So if I shift log both of these, this side here becomes H3O plus. Well, we get this equation here. Okay? H3O plus equals 10 to the negative pH. So if we have a calculator, let's say Casio 9750, right? With that calculator, you'll see that there is a button that's just labeled log. All that you need to do to calculate pH is you type in the concentration of your H2O plus and then press the log button. You'll be given a negative number. After you do that negative number, you need to then press plus minus. So the second equation here we use to find the concentration of H2O plus when we know the pH. So again, in our calculator, we just chuck in the pH in our calculator, we give it a negative sign, and then we do the 10 to the X button, which is the shift of the log button. Okay, so it's the same button as the log button, but we have to press shift to access it. We'll do an example of this on the next slide. You can ask a question. So we have one more equation we have to know here. The equation that we need to know is this one here. But it's the one we did from the previous slide, right? And then the reason we need to know that one is, well, what if someone gave us the OH concentration and we wanted to find the H3O plus concentration? We can use this. So I'll give a couple examples here. So let's find out the pH of strong acid, right? So the first thing we do is, they've given us a question, we've got a concentration of HCl, which is a strong acid. It's 0.0035 moles per litre. Here's the equation for it. Notice because this is a strong acid, it reacts completely, and we know that the concentration of the acid is going to equal the concentration of hydronium ion. So I can write that down. Hydronium ion equals HCl equals 0.0350 moles per litre. Then I can use this fancy equation. pH equals negative log H2O plus. So I'm going to put this number in my calculator, press the log button, and then press the negative sign. And hey presto, we get this number here, 2.46. Now that kind of makes sense, because if I was to write this in standard form, it would be 3.5 times 10 to the negative 3. And our log is, our pH is always the number that is just below the exponent. Okay, so if the exponent here is negative 3, this is going to be 2 point something. If it was negative 8, this is going to be 7 point something. So now we've found our pH, I can actually try something else with this. Oh, if I know the concentration of H2O plus, can I work out the concentration of OH minus? Yes, I can. I can use this equation here, right? No. So if someone asked me, we can also work out the concentration of OH minus, because in the solution, if we've got H3O plus now in my solution, it must be working with the OH minus to produce 1 times 10 to the negative 14. It is a common ion. So now, because we've added this common ion of H3O plus, I can work out what concentration the OH minus have to be so that it equals 1 times 10 to the negative 14. Because the multiplication of these two always equals 1 times 10 to the negative 14. And if I've said my acid equals this number, what is my base equal? Well, I just rearrange this equation, right? So I move the H2O plus to the other side, put it underneath the fraction, and I get 1 times 10 to the negative 14 divided by this equals 2.86 times 10 to the negative 12. Did you know you can actually find out something of this called the POH? The POH? What's that, you say? The POH is just the negative log of this number, of the OH concentration. I'm going to tell you now, if you do the POH of this, the number you're going to get is 11.54. If I was to do the negative log of the OH minus concentration, the number will be 11.54. Now, how do I know? Yeah, it's the POH. If I'm doing the negative log of the OH concentration, it's called the POH. And one really interesting point is the POH plus the pH always equals 14. So if I know the pH, I can find the POH. Therefore, that means if I knew the POH, I could go backwards and find the OH by doing the 10 to the X. Sounds tricky, but once you get used to it, it's not a bad thing to know. Notice the pH, no units, right? Just like KW, there are no units for it, you just chuck it down. Okay, so the next concentration. So this one here is straightforward. If we know the concentration of H2O plus, usually the pH is quite straightforward. However, if I want to find out the pH of a base, strong base, right? Here's an example. Calcium hydroxide, what's its concentration? Right, so I need to first draw an equation. Look at the calcium hydroxide here. For every one of these, I make 2 of these. Right? I haven't balanced this correctly, but there should be a 2 in front of that OH. So you can then say, well, the concentration OH minus is 0.0250 moles per litre. Yes, that's correct. There should be 2 OH. This is a mistake here. So once I've done that, I can now find out the H3O plus. I need to find out the H3O plus. Actually, there's 2 steps, 2 ways to do this. You could right here, right now, find the POH. Right? If you find the POH, you can just take that number away from 14 to find the pH. Or you can chuck the number into this equation here, yeah, and know that H3O plus equals 1 times 10 to the 14 divided by this concentration, and we get a concentration for H3O plus. We then put that into this equation, and we find the pH. No, the pH of the solution is this. Okay, but remember the pH comes from the concentration of the H3O plus. However, if you went up the top here and just worked out the POH, it would have been 2.6, and you just subtract it from 14. It's a lot more straightforward, but you have to get confident in using this equation. So we can practice that, but once we learn things really well, we're just going to learn things like the POH is this, the pH is